Imagine this traveller, you didn't arrive here by accident. Something in the dark pulled you here, a question, a whisper, a quiet sense that the universe is shifting in ways we can barely name. What if an interstellar wanderer could choose to stay? What are the odds that a fragment of another star would slip into a 1 in 20,000 orbit, brushing past Mars, Venus and Jupiter as if following a hidden map? 33 billion tons moving without a sound, a body drifting toward the sun, a light that should not glow yet does. Tonight we follow that mystery together. Listen before you fall asleep beneath the stars. October the 29th had changed everything, though not with drama or alarm. It had changed things the way the cosmos usually did, with quiet numbers, with improbable alignments, with small deviations from what astronomers expected. When Avi Loeb began explaining Threodism Atlas, he had not started with speculation or sweeping theories. He had begun with a measurement 20 kilometres. That had been the early estimate of Atlas's diameter, based on the sunlight it reflected when first detected. 20 kilometres had been larger than Manhattan Island, and roughly twice the size of the asteroid that ended the age of dinosaurs. For something arriving from another star system, that size alone had been unusual. Interstellar space was not filled with mountains. It was filled with fragments, pebbles, ice grains, and occasional shards of rock. A 20-kilometre object wandering into the inner solar system had been statistically rare. Loeb had emphasised this point with simple, careful math. Based on the estimated mass of rocky material drifting between stars, an object as large as Atlas should on average have passed through the inner solar system once every 10,000 years. Yet humanity had only been capable of systematically identifying interstellar objects for about a decade. In those 10 years, astronomers should have detected countless smaller visitors before finding anything that large. The distribution of debris in space followed a power law. Small rocks outnumbered large ones by orders of magnitude. In principle, researchers should have catalogued hundreds of thousands of objects the size of Oumuamua, roughly 100 metres, before ever encountering something with a diameter measured in tens of kilometres. But only 2 small objects had been detected, Oumuamua in 2017 and Borisov in 2019, before Atlas appeared far larger than either of them. It had been possible that smaller objects simply escaped notice, because they were too faint to detect at great distances. Observational bias had always complicated scientific expectations, yet even with those allowances, Atlas had felt early, as though it had arrived ahead of schedule. The brightness of Atlas had deepened the puzzle. When it was first observed on July 1, 2025, it had been beyond the orbit of Jupiter, a region where comets remained dormant and nearly invisible. Sunlight was too weak at that distance to warm their surfaces. True comets only became active inside roughly 5 astronomical units. But Atlas had already been glowing strongly enough that its brightness suggested a massive nucleus. Something had been causing it to shine before it should have. The simplest explanation was that volatile ices on the surface sublimated at unusually low temperatures, but Loeb had noted that this behaviour was rare. The alternative, that the source of the brightness was internal rather than external, had been extraordinary, but he had not asserted it outright. Trajectory had added another quiet anomaly. An interstellar object should not have cared about the orientation of our solar system. It should have arrived from a random angle, a random inclination, preserving the geometry of its home system. Yet Atlas had entered the solar system aligned with the ecliptic plane to within 5 degrees, almost perfectly level with the orbits of Earth, Mars, Venus and Jupiter. Loeb had calculated that this alignment carried a 1 in 500 probability of occurring by chance. Not impossible, but noteworthy. Then had come a more severe improbability. Atlas had passed unusually close to 3 planets, Mars, Venus and Jupiter, each encounter timed precisely with the planets' positions in their orbits. When Loeb calculated the probability that a random interstellar object would achieve all 3 close approaches with such timing, he had arrived at roughly 1 in 20,000. Again, not impossible, but far from ordinary. One improbable feature might have been coincidence. 2 or 3 had begun to resemble a pattern, even if the pattern had no intentional cause. Loeb had not claimed certainty about any of this. His argument had been built not on conclusions but on tensions between expected distributions and observed ones between typical comet behaviour and what Atlas had actually done. He had pointed out that science did not require extraordinary explanations, it simply required noticing when data diverged from norms. If coincidences accumulated, one at least had to acknowledge the accumulation. The brightness beyond Jupiter, the ecliptic alignment, the series of close planetary encounters, each detail might have been explicable on its own. Together they had formed a cluster of low-probability events deserving scrutiny. Loeb had compared it to watching someone roll a die and land 10 times in a row. It could have been chance. The universe allowed rare events. But any rational observer, he said, would have looked more closely at the die. The central theme in Loeb's reasoning had always been humility, not the humility of accepting extravagant claims, but the humility of refusing to ignore anomalies simply because they were inconvenient. The universe had never been obligated to behave ordinarily. It often revealed its surprises first through statistics and only later through clearer signs. Atlas might have been nothing more than a natural interstellar comet, with unusual but ultimately explainable characteristics. Yet it might also have been something rarer, something not captured by current models of interstellar debris. In the face of such uncertainty, Loeb had argued for careful observation, not certainty, attention, not alarm. Humanity had been watching an object whose behaviour diverged from expectations. Whether those divergences mattered remained to be seen. For the moment, the only honest position had been to accept what was unknown and let the data guide understanding as Atlas continued its quiet path toward the Sun, toward October 29th, and toward whatever came after. Loeb had continued by examining the brightness of Atlas in a more methodical way. Most comets only developed visible comae once they passed inside roughly 5 astronomical units from the Sun, but Atlas had begun glowing well before that threshold. It had behaved as though it were already warming, already reacting, already shedding material in a region of space where sunlight was too weak to cause such activity in typical objects. Loeb had treated this not as evidence of something extraordinary, but as another statistical deviation. It had suggested that Atlas either possessed a composition unusually rich in low-temperature volatiles, or that something else, as yet unidentified, had been influencing its behaviour. He had then shifted to the matter of trajectory, a topic that often revealed more about an object's origin than its chemistry. Interstellar objects were expected to enter the solar system on random inclinations, their paths shaped by the gravitational histories of distant stars. Yet Atlas had approached along an orbit aligned within 5 degrees of the ecliptic plane. Loeb had calculated that such alignment occurred in roughly 1 out of every 500 cases for an object arriving from interstellar space. It was not impossible, but it was not the norm. And astronomy, he liked to remind people, was a science in which deviations from the norm often carried meaning. The planetary encounters had compounded this effect. Atlas had approached Mars, Venus, and Jupiter at distances tighter than chance alone predicted. Each planet had occupied just the right segment of its orbit at just the right time. When Loeb combined these probabilities, the result 1 in 20,000 had made him pause. No single coincidence had forced a conclusion, but the pattern had deserved attention. Still, he had not insisted that the trajectory implied intent. He had simply argued that nature sometimes arranged its components in ways that challenged assumptions. In such cases, the responsible response was neither denial nor sensationalism, but careful observation. From here, Loeb had addressed the early size calculations. The 20-kilometre estimate had arisen from the brightness of Atlas at discovery. Over time, as better measurements accumulated, the estimated diameter had decreased to around 5 or 6 kilometres. This reduction had resolved some statistical tension, but not all of it. Even a 5-kilometre object had been large in the context of interstellar debris, and then the mass estimate had complicated matters again. Observations from the James Webb Space Telescope had shown that Atlas was losing mass at a rate of approximately 150 kilograms per second. Yet its trajectory displayed almost no detectable, non-gravitational acceleration. Comets that vented that much material typically veered slightly from their predicted gravitational paths. Atlas had not. Loeb and his colleagues had calculated that the only way to reconcile the mass loss rate with the absence of measurable acceleration was for Atlas to possess a minimum mass of 33 billion tons. That figure had prompted questions. If Atlas were that massive, then it had likely possessed a substantial nucleus. But if it were also undergoing measurable outgassing, why had its trajectory remained so stable? The most conservative answer was that Atlas's bulk simply overwhelmed the thrust generated by its jets of escaping gas. Yet Loeb had pointed out that 33 billion tons was a lower bound, not an upper one. The true mass might have been higher. This in turn had raised the issue of internal structure. A solid object of that size would have been extremely rare but possible. A hollow object, something with a large volume but relatively modest mass, would also have matched the data. Loeb had been careful not to overinterpret this, but he had noted that hollow structures were hallmarks of engineering rather than geology. He had not claimed that Atlas was engineered, only that the mass constraints were compatible with either scenario. He had then returned to the visual anomalies recorded by Hubble and other observatories. Early images had shown an unusual forward-facing glow light extending toward the sun rather than away from it. The explanation offered had been that the glow resulted from motion blur, a byproduct of Atlas's high velocity during long exposures. Loeb had acknowledged that explanation, but had maintained that the brightness distribution in the images did not perfectly match expectations. Later, Atlas had developed a more conventional cometary tail, confirming activity consistent with sublimation. But Loeb had cautioned that an object travelling for millions of years through interstellar space would naturally accrete a layer of ice and dust. Such a layer could produce comet-like features regardless of what lay beneath. The green glow had added complexity. In September, Atlas had suddenly exhibited a vivid green coloration, a phenomenon typically associated with diatomic carbon fluorescing under ultraviolet light. But previous spectroscopic measurements had shown unusually low levels of carbon chain molecules. The abrupt appearance of green suggested either fresh material being exposed or a chemical process not yet understood. Loeb had considered several explanations, including the possibility that cyanide emissions had spiked, but he had noted that the timing resembled a threshold effect, an abrupt transition rather than a gradual increase. Throughout all of this, Loeb had maintained a calm, disciplined approach. He had not insisted that Atlas was anything other than a comet. He had merely observed that it was an unusual one with characteristics warranting sustained attention. The universe, he often said, was under no obligation to behave predictably. Science advanced by examining the exceptions. Atlas's chemistry, its trajectory, its brightness, its mass. Each element had carried its own uncertainty. Yet altogether, they had formed a picture that was neither conclusive nor dismissible. Loeb's position had been simple. The data did not rule out natural explanations, but neither did it demand that they be the only ones considered. Humility required acknowledging the limits of current understanding. In that sense, Atlas had served less as a mystery to be solved, and more as a reminder of how little humanity had explored how vast the universe remained, and how easily our expectations could be reshaped by a single object drifting through the inner solar system. As observations accumulated, the behaviour of Atlas had continued to challenge established models. One of the most surprising aspects involved the chemical composition detected by space telescopes and spectrometers. When the James Webb Space Telescope had captured its early spectra, astronomers had expected to find a mix of volatile compounds, typical of long-period comets, water carbon dioxide, methanol, and traces of organic molecules. Instead, the chemical profile had been sparse and oddly selective. Carbon dioxide had been present, but many carbon-bearing species that normally accompanied it were either absent or present only in negligible amounts. This chemical simplicity had been unusual. Most comets arriving from the Oort cloud or even interstellar space carried a complex mixture of organic molecules formed in the cold molecular clouds where their parent systems had formed. The absence of these compounds in Atlas had suggested that its surface had either been stripped or modified. Loeb had noted that the object's composition seemed processed rather than pristine, though he had not asserted a specific cause. Then there had been the nickel tetracarbonyl anomaly. At one point, spectrometric readings had implied the presence of nickel containing compounds in the coma substances rare in natural environments, but common in industrial processes. Scientists had initially dismissed the signal as a calibration error, but after repeated verification, the reading persisted. Although Loeb had not claimed any artificial origin, he'd pointed out that nickel tetracarbonyl was a molecule that decomposed rapidly under solar radiation. Its detection near Atlas implied that the compound had been produced recently, and near the object itself. No natural mechanism had been proposed that satisfactorily explained its abundance. Meanwhile, astronomers had continued tracking Atlas's trajectory as it approached perihelion. The object's path had remained extraordinarily precise. Even after accounting for gravitational interactions with the Sun and planets, Atlas had maintained an unusually stable orbit. This stability had been inconsistent with its level of outgassing. Traditionally, when jets of sublimating material expelled from a comet's surface, the resulting thrust altered the comet's motion slightly. But the trajectory of Atlas had matched pure gravitational models almost perfectly. The only model that matched the observations required the comet to be far more massive than originally estimated, a constraint that reinforced the earlier 33 billion ton estimate. As Atlas had drawn closer to the Sun, the issue of outgassing grew more complicated. Photometric data captured fluctuations in brightness that did not follow the gradual curve expected from standard thermal models. Instead, Atlas's activity had spiked abruptly at specific distances, as though triggered by sudden structural changes or exposure of fresh material. This behaviour had resembled threshold effects, not smooth sublimation. Loeb had compared it to a layered object shedding surface coatings as internal sections encountered solar heat. The alignment of these brightness spikes with specific distances from the Sun had also drawn attention. Several occurred when Atlas crossed orbital resonances or regions of increased solar flux, suggesting either structural complexity or compositional layering. None of these explanations contradicted natural comet physics, but they did complicate them. During this period, telescopes worldwide had attempted to capture detailed images. Long exposures of Atlas taken by Hubble had produced a puzzling pattern, a faint forward glow seemingly extending ahead of the nucleus in the direction of motion. Analysts had attributed this to motion blur from Atlas's high velocity and the constraints of long exposures. Loeb had accepted that explanation, but had noted that the brightness distribution did not match typical modelling results. The forward-facing luminosity had appeared more concentrated and symmetrical than expected from pure streaking. Ground-based telescopes had captured similar anomalies. One set of observations from Chile had shown a slight asymmetry in the coma, something resembling a crescent shape, rather than the traditional spherical halo. While many comets produced a symmetrical comia due to localized jets or rotation, the symmetry of Atlas's crescent had been unusually clean. Several astronomers had commented that it resembled a structured outflow, rather than the chaotic spray seen in natural jets. By the time Atlas approached the inner solar system, attention had shifted to its upcoming conjunction with the Sun. For several weeks, Atlas would pass behind the Sun from Earth's perspective, rendering it unobservable by telescopes on or near our planet. Loeb had pointed out that this period of invisibility presented an excellent opportunity for nature, or for any hypothetical mechanism to alter its trajectory without immediate detection. His point had not been that such a change would happen, but that astronomers would be unable to verify the object's course until it re-emerged in December. The timing of the solar conjunction had itself been noted by Loeb with characteristic caution. Atlas had approached perihelion at precisely the moment that ensured maximum observational blind spots from Earth. Statistically, this alignment had carried no meaning. Many objects passed behind the Sun on their way around it. But combined with the sequence of improbable alignments leading up to it, the conjunction had become one more feature in a growing cluster of anomalies. Throughout all of this, Loeb's commentary had remained measured. He had advocated neither fear nor fascination, only attention. He had reminded audiences that science progressed not by confirming expectations, but by examining the exceptions. Atlas, in his view, had simply been an exception worthy of rigorous study. It had forced astronomers to confront the limits of their models, and consider whether the distribution of interstellar objects was more complex than previously believed. In the weeks leading up to October the 29th, Atlas had become a kind of mirror reflecting not only sunlight but the assumptions embedded in modern astronomy. Whether it turned out to be a natural comet with unusual properties or something that demanded new theoretical frameworks, it had already achieved one scientific purpose. It had forced humanity to look more closely at the statistical landscape of the universe and acknowledge how much remained unexplored. As the days progressed toward perihelion, another issue had emerged: the uneven flow of data from the world's space agencies. In early October, the European Space Agency released a set of low-resolution images captured by the ExoMars Trace Gas Orbiter. These images had shown little more than a white blur, an unresolved point of light barely distinguishable from background stars. The scientific value was limited and public reaction had been frustrated. Many amateur astronomers had noted that backyard telescopes operating at far greater distances from their targets routinely produce sharper images of ordinary comets. What drew attention was not the quality of the ESA images, but the absence of images from more capable spacecraft. NASA's Mars Reconnaissance Orbiter housed HiRISE, the highest resolution camera ever sent to another planet. China's Tianwen-1 carried capable imaging instruments of its own, as did the UAE's HOPE probe. All three spacecraft had been in favourable positions during Atlas's closest pass to Mars, yet none of them had released their data. Initially, NASA had cited the US government shutdown on October 1st as the reason for delays. With thousands of employees furloughed, routine data processing and public communications had paused. But this explanation had quickly come under scrutiny. ESA, which was unaffected by US political deadlock, still released only low-grade images. China, known for using every opportunity to showcase its space program, remained silent. The UAE, typically eager to publicize accomplishments from its first interplanetary mission, also withheld its data. This synchronized silence had raised questions. It was possible that the images were simply underwhelming or that they required extensive processing. But the absence of even basic releases had struck many observers as unusual. Loeb himself had remarked that independent verification was essential and that delayed data inhibited scientific progress. Still, he had refrained from implying ulterior motives. Instead, he argued that the lack of imagery underscored another point: humanity was still dependent on narrow observational windows and vulnerable to bureaucratic interruptions at critical moments. Meanwhile, Atlas's unusual activity continued. Amateur astronomers attempting to image the object reported inconsistent results. Some recorded a faint smooth halo. Others captured what appeared to be asymmetrical structures, shapes that after heavy digital processing resembled angular protrusions rather than typical diffuse patterns. The scientific community generally attributed these anomalies to overprocessing equipment limitations or atmospheric distortions. Loeb had cautioned that interpreting compressed or enhanced imagery was dangerous. The human brain was adept at finding patterns where none existed. However, he also acknowledged that the consistency of certain shapes across independent observers was intriguing and warranted proper investigation once higher quality data became available. Spectroscopic measurements from ground-based observatories revealed additional surprises. The intensity of certain emissions fluctuated rapidly over short periods, far faster than thermal models predicted for a comet of Atlas's size. These fluctuations suggested that Atlas's surface chemistry was not uniform or that localized jets were turning on and off as the nucleus rotated. Yet rotational signatures were weak. The object's light curve did not show the regular periodic dimming and brightening expected from a tumbling or spinning body. This inconsistency had complicated modelling efforts. By mid-October, Atlas had brightened again. The green glow associated with diatomic carbon had reappeared with greater intensity, but this time spectroscopic analysis indicated an unusual ratio between carbon emissions and the overall brightness of the coma. The green signature was strong even when the object's visible light had not increased proportionally. Loeb had noted that such decoupling was rare in natural objects. It implied either a sudden exposure of fresh material or a previously unseen chemical process. As Atlas neared the Sun, solar-wind interactions became more pronounced. Instruments sensitive to charged particles detected irregularities in the solar wind near the object. Some researchers interpreted these as ordinary disturbances caused by Atlas's outgassing. Others argued that the variations were too coherent and sustained to be explained solely by gas emissions. The data were incomplete, and interpretations varied widely. Throughout these developments, Loeb's stance had remained consistent. he reminded audiences that anomalies were not conclusions. They were only signals pointing to areas where existing models might be incomplete. Atlas had highlighted several such areas: mass distribution, chemical composition, non-gravitational forces, brightness behavior, and orbital geometry. Each anomaly had been capable of natural explanation, but taken together they formed a pattern that was statistically uncommon. As the final week before perihelion approached, the tone of scientific discussion shifted. The unknowns had accumulated, but so had the desire for clarity. Many astronomers hoped that the object's behavior near the Sun would resolve outstanding questions. Comets often revealed their internal composition when heated intensely. If Atlas were an ordinary comet, its approach to the Sun should have triggered predictable physical responses. Yet Loeb had noted that if Atlas possessed any stable internal structure, natural or otherwise, it might behave differently. Its outgassing profile could change abruptly. Its trajectory could shift slightly. Its coma could expand or collapse. Or it might show nothing unusual at all and simply continue along its predicted path. What concerned researchers most was the month-long observational blackout. Once Atlas passed behind the Sun, Earth-based observatories would be unable to track it until early December. During that interval, any changes in velocity or direction would go unnoticed. When the object reappeared, scientists would compare its new trajectory with predictions. A deviation would indicate that non-gravitational forces or something more exotic had acted upon it. No deviation would imply that natural processes had dominated. Either outcome had scientific value. But the uncertainty combined with the anomalous features observed up to that point had turned Atlas into one of the most closely watched objects in modern astronomy, despite the fact that for several weeks it would not be visible at all. As October drew to a close and Atlas entered the final stretch toward the Sun, conversations among researchers grew more restrained. The object's increasing proximity made it difficult for even space telescopes to capture clean data. Scattered light from the solar corona overwhelmed sensors, producing streaks and flares that complicated interpretation. Some observatories attempted to adjust their exposure algorithms, but the results remained noisy. By October 25th, most ground-based teams had conceded that meaningful imaging would halt until Atlas emerged from behind the Sun weeks later. The final pre-conjunction observations revealed subtle but notable changes in the coma. The green emissions persisted but fluctuated in irregular pulses, rising and falling on timescales of minutes rather than hours. Normally, sublimation responses to solar heating evolved gradually following thermal diffusion patterns. The rapid oscillations suggested either localized jets venting in brief intervals or surface patches with sharply varying compositions. Neither explanation fit comfortably. No rotational period had been confidently established, and without it, mapping these pulses to surface features became guesswork. Meanwhile, solar wind instruments detected a faint but continuous distortion in the flow around Atlas. Plasma waves, normally chaotic near a heated comet, showed partial coherence, as though the object projected a subtle shape into the passing stream. Some argued this was simply the result of an unusually symmetric coma, while others speculated that Atlas's mass distribution produced an atypically smooth interaction. Models struggled to replicate the observed structure. Each attempt required parameters that deviated from those typical of known comets. The discrepancies were small individually but persistent. On October the 27th, 2 days before, perihelion communication teams from several observatories attempted coordinated spectroscopic measurements, hoping that simultaneous sampling might extract a cleaner signal. The effort produced mixed results. One observatory detected a steep rise in cyanide emissions consistent with previous trends. Another detected barely any increase at all. A third observed a temporary shift in the coma's central brightness peak, implying either a rotation event or a sudden collapse of one outgassing region. No consensus formed. The data were too fragmented, the viewing angles too poor. As the final hours approached, a quiet tension settled over the global astronomical community, not dramatic or alarmist, but contemplative. Everyone understood the significance of the moment. Once Atlas slipped behind, the Sun, Earth would lose all direct contact with it. The largest gap in observations since its discovery would begin, and whatever occurred during that interval would remain hidden. Researchers expected nothing extraordinary, but they acknowledged the weight of the unknown. Orbital mechanics often felt deterministic and predictable. Yet here was a visitor from another star system approaching the one place in the sky where prediction could not be immediately verified. When the moment finally arrived, Atlas passed behind the Sun with no fanfare. No instrument captured a definitive final image. The last confirmed detection was a faint smear recorded by a space-based solar observatory barely distinguishable from coronal noise. Observers marked the timestamp, checked the expected trajectory once more, and waited for the inevitable fall-off in signal. Then the silence settled in. It was a familiar silence, the kind that accompanied every solar conjunction. But the extended duration made this one feel heavier. For nearly a month, the object would remain beyond reach. Analysts would run simulations, update uncertainty estimates, and prepare observational campaigns for December, but no new data would arrive. The object's fate, its trajectory, its state of activity, its physical integrity would remain unknown until the Sun released its grip on the line of sight. In that absence, attention shifted toward the future. Teams began drafting new observing proposals for when Atlas reappeared. The combined use of Hubble Webb and large ground-based telescopes would aim not only to capture high-resolution imagery, but also to measure its post-perihelion velocity with exceptional precision. If Atlas behaved like an ordinary comet, its trajectory would match predictions closely. Minor deviations were expected due to asymmetric outgassing. Larger deviations on the scale of kilometers per second or shifts in orbital inclination would raise deeper questions. Some researchers prepared contingency models. They mapped the possible post-conjunction positions of Atlas and assigned probabilities to each. Most scenarios placed it on a clear outbound path. A smaller subset predicted slight variations. A very small fraction, barely above numerical noise, predicted changes large enough to indicate non-gravitational impulse, though unlikely they were included for completeness. Modelers understood that excluding low-probability outcomes had historically caused scientific blind spots. Public interest did not fade during the blackout period. News articles speculated about what might be happening behind the Sun. Some fixated on the lack of high-resolution images from Mars' orbit, others questioned why agencies had not prioritized additional observations earlier in the month. Scientists responded with cautious statements. They emphasized the limits imposed by geometry instrument constraints and mission priorities. They also reiterated that nothing in the data required extraordinary explanations. Loeb, for his part, maintained a measured tone. He reminded audiences that the absence of data was simply that, an absence, not a revelation. The true test would come after conjunction. He also reiterated that scientific inquiry was not a contest between natural and artificial explanations. It was an attempt to understand unfamiliar phenomena using all available evidence guided by both skepticism and curiosity. If Atlas reappeared exactly where predicted, that would strengthen the case for a natural interpretation. If it did not, the implications would merit deeper examination. In private notes released later, several astronomers described the conjunction period as strangely reflective. Without new images or measurements to analyze, they found themselves thinking about the broader context. Humanity had observed only 3 confirmed interstellar objects. Each had behaved differently. Oumuamua had accelerated mysteriously. Borisov had fragmented violently. Atlas had arrived with a cascade of minor but cumulative anomalies. Perhaps the diversity itself revealed something important, that interstellar space contained more variety than models had assumed. Or perhaps observational biases had shaped their perceptions more than they realized. As November advanced, the anticipation grew. Observatories recalibrated their instruments. Researchers adjusted their schedules. Amateur astronomers prepared to scan the early morning sky. The moment of reappearance would be subtle, a faint dot emerging from solar glare detected first, not by the eye, but by algorithms tuned to pick out slow-moving objects. Everyone knew what they were waiting for: a single data point, a single coordinate in the sky. If that point aligned with predictions, the mystery would begin to settle. If it did not, the questions would deepen. Either way, humanity would learn something new the moment Atlas stepped back into the light. When Atlas finally emerged from behind the Sun, it did so quietly. The first detection came not from a major observatory, but but from a modest solar monitoring instrument designed to track coronal mass ejections. Its image was grainy, compromised by solar interference and nearly dismissed as noise. Only after automated software flagged a faint, slowly drifting point did analysts look closer. The coordinate matched one of the mid-probability predictions, neither the most conservative nor the most extreme. It was enough to confirm the object had survived perihelion, but not enough to reveal anything about its trajectory or physical state. Within hours, larger observatories began turning their sensors toward the predicted region of the sky. Hubble obtained the first reliable post-conjunction exposure. The nucleus appeared intact, the coma faint but present. There was no evidence of fragmentation or dust shedding, which had been one of the expected outcomes given the thermal stress near perihelion. The object had endured the encounter in a surprisingly stable form. Researchers compared its brightness profile to pre-conjunction values. The change was smaller than anticipated. Comets typically dimmed sharply after perihelion, as volatile materials depleted. Atlas, however, retained significant luminosity, suggesting either an abundant reservoir of volatiles or an unusually insulating surface. The next priority was velocity measurement. Teams analysed successive exposures to derive its angular motion, then combined those values with known parallax baselines to estimate speed. The early calculations produced a range broad enough to be inconclusive. Some values aligned well with the pre-perihelion trajectory, while others hinted at slight deviations. Everyone knew the initial numbers would require refinement, but even minor inconsistencies attracted attention. Analysts debated whether the deviations resulted from observational noise errors in centroiding the nucleus or subtle outgassing forces. Over the following days, multiple observatories contributed data, gradually tightening the uncertainty margins. The refined trajectory appeared to fall just within the natural expectations, but only just. The outbound path arced slightly shallower than the inbound one. The difference was small enough to remain compatible with asymmetric sublimation, yet large enough that it could not be dismissed outright. Researchers recalculated non-gravitational parameters, comparing them to known comets. Atlas's values remained unusually low, consistent with previous findings. If outgassing had caused the deviation, it seemed to have done so with remarkable efficiency relative to the object's mass. Spectroscopic teams soon weighed in with their first post-conjunction results. The chemical signature had changed. Cyanide levels previously high were now reduced. Carbon dioxide emissions remained strong but declined more gradually than water vapour. The ratios did not match a standard depletion curve. They resembled in some ways the chemical evolution of long-period comets, except Atlas was not bound to any star system. Its chemistry remained a puzzle neither implausible nor easily categorized. While scientists worked through the data, the public discussion resumed. Some observers treated the survival of perihelion as an expected milestone. Others built narratives around the minor trajectory discrepancy. Science communicators urged patience, explaining that comets frequently exhibited small course variations after perihelion. Thermal jetting, vent openings, and rotational changes contributed to such effects, but those same communicators acknowledged that Atlas's mass and the lack of significant non-gravitational acceleration prior to perihelion made the deviation more difficult to interpret cleanly. Amid these discussions, attention shifted toward the upcoming closest approach to Earth, still distant, still millions of kilometers away, but close enough to enable detailed imaging. Preparations intensified. Observatories scheduled dedicated time blocks. Data pipelines were redesigned to accommodate higher frequency monitoring. The goal was to track Atlas continuously across its outbound arc, observing every photometric fluctuation and every spectral nuance. Some teams proposed using radar, though the distance made that improbable. Others advocated for coordinated interferometry to maximize resolution. Meanwhile, researchers at the Mars Reconnaissance Orbiter released their processed imaging from the earlier flyby. The data, though limited in resolution, helped refine the nucleus size estimate yet again. The results narrowed the nucleus to a range between 5 and 8 kilometers, still large but smaller than the earliest estimates. The images provided no evidence of geometric structure. The nucleus appeared irregular, consistent with an icy body. However, the coma exhibited a subtle asymmetry that analysts struggled to model. It suggested a consistent directional bias in outgassing. but the source region remained uncertain. The combination of all these observations produced a portrait that was neither mundane nor extreme. Atlas continued to defy easy classification. Each anomaly had a possible explanation, yet their collective presence maintained a sense of incompleteness. The object fit the comet model in broad strokes, but the details diverged in ways that resisted simple reduction. Researchers found themselves revisiting earlier assumptions not to overturn them, but to reassess the margins. The history of astronomy had taught them that unusual objects often forced refinement of models, not abandonment. By mid-December, the object grew bright enough for naked eye detection under dark skies. Small telescopes captured its modest tail. Amateur astronomers shared images showing a delicate green tint along the coma's edge, a remnant of the earlier spectral behaviour. The public fascination surged. For many, the object symbolised both the vastness of the universe and the limits of human knowledge. It was a visitor from another star system, a factual statement that needed no embellishment to provoke wonder. As the date of closest approach approached, scientific interest reached its peak. Teams sought to finalise their refined post-perihelion models. Some predicted a gradual decline in brightness as Atlas moved farther from the Sun. Others suggested the object might maintain higher luminosity than predicted given its earlier behaviour. Chemically, the ratios might stabilise or drift toward more typical comet patterns. Dynamically, the outbound trajectory would confirm whether the slight deviation was meaningful or merely an artefact of early post-conjunction uncertainties. Everyone prepared for the final round of observations before Atlas receded into the outer solar system. The opportunity would not return for centuries, if at all. Whether the object ultimately conformed to expectations or continued to diverge from them, the data collected during this period would shape scientific understanding of interstellar visitors for decades to come. And so, as Earth moved slowly along its orbit, and Atlas drifted outward along its own, the stage was set for the final phase of its passage, a phase not defined by anticipation of what might be hidden, but by direct observation of what remained to be seen. As Atlas moved into the weeks surrounding its closest approach to Earth, the observations became more consistent and more detailed. The improved geometry allowed telescopes to track the nucleus with far greater accuracy, and for the first time since its discovery, researchers began to feel that the object's true behaviour might finally be within reach. The uncertainties that had dominated the post-conjunction period narrowed steadily. Its orbit, though still slightly shallower than pre-perihelion predictions, stabilised into a coherent outbound curve that aligned well with gravitational models. The discrepancy persisted, but diminished to the level where many analysts considered it marginal, rather than transformative. Brightness measurements revealed another interesting trend. Atlas's luminosity decreased more slowly than expected. A natural decrease always followed perihelion, as volatiles depleted, yet its decline occurred at an unusually gentle rate. Spectroscopists noted that carbon dioxide emissions continued to dominate, with water vapour declining more sharply. The pattern suggested that subsurface layers rich in CO2 remained accessible to solar heating, supporting sustained outgassing even as the nucleus drifted farther from the Sun. Some researchers proposed a thermal lag effect, where deeper layers underwent delayed sublimation. Others suggested that the object's thermal conductivity differed from standard cometary materials. Rotational data remained inconclusive. Analysts observed subtle variations in coma shape hinting at a multi-hour rotation period, but no consensus formed. The scattering of light across the coma complicated interpretation. Attempts to model rotational behaviour using brightness periodicity produced ambiguous results, as outgassing jets introduced noise into the signal. Some teams argued the nucleus might be rotating irregularly, perhaps influenced by uneven mass distribution or past fragmentation events. Others recommended waiting for the object to dim further when the coma thinned and the nucleus could be isolated more reliably. During the closest approach, the James Webb Space Telescope captured its most detailed spectra yet. The instrument recorded clear signatures of carbon monoxide, faint traces of methanol, and a surprising but consistent absorption feature near wavelengths associated with complex organics. The feature was weak and could be noise, but it generated interest because similar signatures had appeared in earlier spectra taken by ground-based observatories. Analysts cautioned that such features were common in primordial ices. Their presence did not imply anything exotic, only that the object had likely formed in a cold region of its home system. Yet the consistency across instruments reinforced the idea that Atlas carried a distinct chemical profile compared to most comets in the solar system. Simultaneously, the object's coma exhibited a persistent asymmetry. Models attempted to match the shape using combinations of jets at various latitudes and longitudes on the nucleus. None fit perfectly. The asymmetry remained stable over multiple days, suggesting a sustained pattern rather than random venting. Some speculated that the distribution of volatiles across the surface might be strongly uneven, perhaps a result of its interstellar journey, during which micrometeoroid impacts, cosmic radiation, or thermal cycling could have altered the surface in irregular ways. By late December, the outbound trajectory had become sufficiently clear to rule out any large-scale maneuver or deviation during the hidden perihelion window. The object behaved like a massive body, influenced primarily by gravity. Its velocity decreased exactly as expected for an interstellar object exiting the inner solar system, and its path curved steadily toward the outer regions where solar influence weakened. Analysts compared inbound and outbound arcs using detailed numerical integration. The curves differed slightly, but the variations were consistent with asymmetric outgassing and did not require extraordinary interpretations. Even so, the object retained an air of uniqueness. The combination of mass estimates, low non-gravitational acceleration, early brightness, anomalies, unusual chemistry, green emissions, and tight planetary encounters created a data set that remained difficult to categorize. None of the features violated physical laws. None required the introduction of artificial explanations. However, their cumulative presence placed Atlas near the edge of known comet behavior rather than firmly within established norms. Public interest peaked again during the final week of December, as amateur astronomers posted their last images before the object dimmed beyond reach. Discussions shifted toward legacy rather than speculation. Scientists reflected on the unprecedented nature of observing an interstellar object in such detail. They recognized that Atlas had become a reference point, a case study that future discoveries would be compared against. The object's behavior highlighted the complexity of interpreting interstellar visitors, especially when data were fragmented across multiple observational windows. As Atlas drifted toward the outer solar system, its coma steadily thinned. By early January, high-resolution telescopes could isolate the nucleus more reliably, but the reduced brightness limited meaningful spectroscopy. Analysts shifted focus from chemical characterization to dynamical modeling, aiming to refine mass estimates one final time. Updated calculations placed its minimum mass slightly higher than earlier post-conjunction values, reinforcing the idea that Atlas belonged on the heavier end of the comet mass spectrum. Some argued the object might be denser than typical comets. Others proposed that its shape or distribution of volatile reservoirs influenced mass estimates indirectly. Regardless of interpretation, researchers agreed the object was now entering a phase where observations would yield diminishing returns. It would remain trackable for several more months, but primarily as a faint moving point, its detailed structure concealed by distance. Eventually it would fade into the background, joining the countless interstellar objects that traversed the galaxy unnoticed. Its outbound path would carry it into regions where only deep survey observatories might detect it if they chose to look. By the time most observatories logged their final meaningful data, Atlas had already become a subject for long-term study rather than active monitoring. Its trajectory would be stored in catalogues, its spectra would be archived, its anomalies would continue to fuel research papers and comparative analyses. But the visitor itself continued outward indifferent to the questions it left behind. In the end, Atlas offered a clear lesson, though not a conclusive answer. Interstellar objects could be familiar, yet strange, predictable, yet subtly unique. Each one carried fragments of its origin system, chemical clues, structural histories and trajectories shaped by forces remote from the Sun. Studying them required a balance of caution, open-mindedness and humility. No single observation could define them, and no single explanation could encompass all possibilities. Atlas demonstrated that the universe often presented complexities that did not fit neatly into existing categories, and that understanding emerged gradually refined through data rather than assumption. As Earth continued along its orbit and winter settled in across much of the planet, the object that had ignited so much curiosity grew dimmer and smaller in the telescopic field. Researchers archived their findings, prepared publications, and transitioned their attention to new targets. But Atlas remained in the background of ongoing discussions about interstellar matter, planetary system formation, and the limits of observational inference. Its passage had been brief by cosmic standards, yet significant for the perspective it offered. By the time it faded beyond practical observation, Atlas had become a reminder of the vastness of the galaxy, an emissary of distant origins carrying a history incompletely understood, and a trajectory that would carry it back into the deep, silent spaces between stars. As Atlas moved farther from the inner solar system, the tone of the scientific conversation shifted from active monitoring to retrospective analysis. The object had passed through the regions where detailed imaging was possible, and with each passing week the returning photons arrived weaker, stretched by distance and diluted by the expanding coma. Observatories continued to log positional data, but the frequency of measurements declined. Teams that had once processed new images daily now coordinated only occasional updates. The object's certainty of survival removed much of the tension surrounding its passage, replacing it with the quieter task of interpretation. The first comprehensive models began to appear in preprint archives. Researchers synthesized inbound and outbound measurements, integrating them with chemical and photometric data. One team focused on the early brightness anomaly, arguing that the unexpectedly strong inbound luminosity could be explained by an extensive halo of fine dust liberated during the object's journey through interstellar space. According to their simulations, the dust could have accumulated gradually as micrometeoroid impacts fractured the surface and produced a persistent debris cloud bound weakly to the nucleus. Sunlight reflecting off this cloud at large, heliocentric distances would have inflated early size estimates. As the object neared the Sun, thermal activity could have reorganized the coma, drawing the dust closer and reducing the effective cross-sectional area, thereby lowering the inferred diameter. The argument did not solve every discrepancy, but it provided a plausible mechanism consistent with physical principles. Another group published a detailed analysis of the object's non-gravitational acceleration. They modelled various geometric distributions of volatile-rich regions on the nucleus, attempting to reproduce the extremely low acceleration observed. Their conclusion proposed that the nucleus might have possessed a combination of low thermal conductivity and deeply buried volatile pockets causing outgassing to occur in infrequent directional episodes, rather than a continuous jetting pattern. These episodic vents, if balanced across the surface, could produce minimal net acceleration. While the model required specific surface conditions, it did not require invoking mechanisms outside the known behaviours of comets. A third team examined the close planetary encounters. They noted that although the probability of such alignments was low, probabilistic arguments often created misleading impressions when applied to rare events. They emphasized that interstellar objects observable with current methods represented only a small fraction of the total population, specifically those entering geometries conducive to detection. Because of this bias, objects passing near the ecliptic plane or near planets were disproportionately represented. The authors argued that Atlas's trajectory appeared unusual only because the underlying population of interstellar objects remained poorly understood. With more detections, distributions might reveal patterns that currently seemed improbable. Yet not all analyses sought to reduce every anomaly to familiar processes. Some researchers acknowledged that Atlas challenged existing assumptions in subtle but significant ways. In their view, each natural explanation depended on specific parameters, and although none violated physical laws, the cumulative precision required suggested gaps in current understanding. This perspective did not imply artificiality. Rather, it pointed toward the diversity of conditions under which interstellar objects formed. Planetary systems across the galaxy varied widely in chemical composition, thermal environments, and dynamical history. The differences observed in Atlas might reflect an origin in a region colder or more carbon-rich than any found in the solar system. As debates continued, attention turned toward the object's long-term trajectory. Numerical integrations projected its path thousands of years into the future. Atlas would not return. Its outbound speed remained higher than the escape velocity required to leave the solar system permanently. The shallow post-perihelion deviation did not alter that fundamental fact. Eventually it would cross the heliopause, re-enter interstellar space and continue drifting through the galaxy. Its next encounter with the star system might occur millions of years from now, if at all. Humanity's brief opportunity to study it had come and gone. With the object's departure, the broader implications came into sharper focus. Atlas represented only the third confirmed interstellar object, yet it behaved differently from both of its predecessors. Oumuamua had exhibited a puzzling acceleration and lacked a visible coma. Borisov had resembled a traditional comet, but fragmented violently. Atlas combined elements of both while adding its own set of unusual characteristics. The diversity suggested that interstellar populations encompassed a wider range of structural and chemical profiles than previously assumed. This realization had practical consequences. Observatories, planning future detection strategies, adapted their algorithms to account for the variations highlighted by Atlas. Some teams revised their criteria for flagging anomalous brightness patterns. Others incorporated new spectral expectations based on the object's unusual volatile ratios. Survey pipelines became more flexible, prepared to identify objects that deviated from standard solar system comet models. Atlas, without intending to reshape the observational approach used to study its successors. In academic circles, discussions focused increasingly on the limitations of inference. Atlas illustrated how easily early assumptions such as size density or chemical composition could shift as new data accumulated. It demonstrated the difficulty of interpreting incomplete records, especially when observations depended on vantage points, interrupted by solar conjunctions. It highlighted the value of coordinated multi-instrument campaigns and the importance of treating anomalies as opportunities rather than nuisances. In this sense, Atlas served as a case study in scientific humility. The object neither confirmed extraordinary hypotheses nor fully conformed to ordinary expectations. Instead, it occupied an ambiguous space that required careful reasoning and restraint. By spring, most observatories had removed Atlas from their active schedules. The object remained traceable, but the scientific returns diminished to the point where new data added little to existing models. Researchers finalized their analyses and prepared public reports summarizing their findings. The conclusions were measured. Atlas likely originated in a cold, carbon-rich region of a distant star system. Its mass was high, but within the range of plausible natural objects. Its trajectory, although statistically uncommon, fell within probabilistic bounds. Its chemical and photometric behavior reflected a combination of unusual surface composition and environmental history. In short, it remained a natural object complex, interesting but not inexplicable. Yet even these conclusions contained caveats. Many papers acknowledged that some uncertainties would persist indefinitely. The exact nature of the forward-facing glow, the precise structure of the coma, and the full composition of the nucleus remained partly unresolved. Much of the object's behavior occurred during periods when Earth had limited or no visibility. The missing data created unavoidable blind spots. No matter how advanced the analysis, interpretations would always rest on models constrained by what could be observed from a single vantage point in a single moment of cosmic time. In the end, Atlas became part of the growing foundation of knowledge about interstellar visitors. It marked an incremental step, neither revolutionary nor trivial. It demonstrated that the galaxy contained objects unlike those formed in the solar system, yet still governed by familiar physics. It revealed that anomalies often reflected the limits of human instruments, rather than the limits of nature, and it prepared astronomers for a future in which such visitors would no longer be rare. Even as the object faded beyond the reach of telescopes, the questions it raised continued to influence ongoing research. The next interstellar visitor would be studied with sharper tools informed by a deeper understanding and interpreted through a lens refined by the lessons of Atlas's passage. As Atlas receded into the outer solar system, the scientific community gradually settled into a more reflective phase. The active monitoring period had ended, but the analyses it inspired continued to evolve. Researchers assembled workshops and conferences dedicated to interstellar objects using Atlas as a central reference. The discussions were not framed around its anomalies alone, but around what those anomalies implied for the broader field. One of the principal themes that emerged was the recognition that existing detection methods were inherently biased. Surveys tended to identify objects whose trajectories passed near the ecliptic, whose brightness profiles matched typical cometary patterns, or whose approach angles favoured extended observation windows. Atlas had fit some of these criteria, but diverged sharply in others, revealing gaps in the current detection paradigm. Several teams recommended expanding search algorithms to include less conventional luminosity curves and more complex motion signatures. Even small improvements could help identify objects approaching from high inclinations or with unusual coma structures. Another line of inquiry examined the implications of Atlas's mass and density estimates. Although the object's minimum mass was well constrained, its true density remained uncertain. The divergence between expected comet densities and Atlas's potential values raised questions about how planetesimals formed in different star systems. Some researchers proposed that interstellar comets might evolve distinct internal structures due to prolonged exposure to cosmic rays, thermal cycling in interstellar space, or repeated encounters with micrometeoroid streams. These processes, largely absent within the protective bubble of the solar system, could produce cores more compact or chemically stratified than anything known locally. As studies accumulated, a gradual shift occurred in how scientists conceptualized interstellar objects. Rather than treating them as outliers, researchers began viewing them as natural components of a much larger galactic ecosystem. In this framework, objects like Atlas acted as messengers from distant planetary nurseries. Each carried a fragment of its origin, encoded in its volatile inventory, structural evolution, and orbital history. By comparing the properties of multiple such visitors, astronomers hope to reconstruct a broader picture of planetary formation beyond the Sun. In parallel, a new generation of survey tools emerged. The Vera Rubin Observatory's wide-field scanning capabilities allowed it to detect fainter and faster-moving objects than its predecessors. Space-based infrared telescopes provided complementary detection opportunities, especially for interstellar objects with low albedo. Atlas influenced the design of these systems more than expected. Its early brightness, unusual chemistry, and complex coma behavior served as specific test cases for refining detection pipelines. The object's trajectory with its unexpected planetary encounters motivated better modelling of inbound dynamical signatures. Even the extended period of lost visibility during solar conjunction encouraged discussions about deploying heliocentric spacecraft in more diverse orbital positions to ensure continuous monitoring. Over time, the discourse around Atlas's anomalies took on a more philosophical tone. Many researchers acknowledged that some uncertainties would remain unresolved permanently. The object had passed through regions where no instruments were positioned to observe its behaviour. Its perihelion passage in particular left a gap that no simulation could fully reconstruct. The scientific literature reflected this humility. Conclusions were stated cautiously, uncertainties quantified meticulously, and explanations framed as probabilistic rather than absolute. Atlas became a reminder that astronomy often operated on the edge of what could be known. A few researchers continued exploring more speculative interpretations, but their arguments gradually shifted. Instead of proposing exotic explanations, they focused on the epistemic challenges of interpreting limited data. They argued that scientific models were always constrained by incomplete observations, and that the appearance of anomalies often reflected the limits of the models rather than violations of physics. In this view, the true significance of Atlas lay not in any single measurement, but in the interplay between observation and interpretation. It exemplified the need to question assumptions, refine methodologies, and remain open to possibilities without abandoning rigor. As the months passed, the object grew too faint for even the most advanced instruments. Eventually, it disappeared entirely from practical observation. Its coordinates remained predictable through ephemerids, but no new photons arrived from its diminishing form. In the absence of real-time data, the object slipped into a different category, no longer an active subject of study, but a reference point in the history of interstellar research. Its trajectory chemical signatures and mass estimates became part of textbooks, lectures, and future proposals. Researchers trained new algorithms using its data. Graduate students built dissertations around its peculiarities. The object itself had moved on, but its influence persisted. In time, as new interstellar visitors appeared, some faint, some bright, some unremarkable, some unexpected. The memory of Atlas served as a grounding context. Its anomalies were no longer viewed as singular curiosities, but as part of a growing catalogue of interstellar diversity. Patterns emerged gradually, not in dramatic revelations, but in incremental refinements to models and in improved detection strategies. Each new visitor added another piece to the puzzle, and the field expanded organically. By then, Atlas existed only as a dim, unreachable traveller continuing along its outbound vector toward the vast, unlit regions beyond the heliosphere. Its surface cooled, its coma dissipated. Whatever internal structure it possessed fell quiet under the deep cold of interstellar space. The object resumed the long, slow drift that had once brought it near the Sun, a trajectory shaped by no intention, governed by no design, merely the outcome of gravitational histories across cosmic distances. For the scientists who had studied it, Atlas remained a case study in the complexity of interstellar objects. It had reminded them that the universe rarely provided complete information, that anomalies often resided at the boundary between data and interpretation, and that humility remained essential in the face of vast unknowns. In its silence, the object left behind a larger legacy, a more sophisticated framework for studying the next visitor and the next after that. And so long after the last telescope lost sight of it, Atlas continued its journey outward, unchanged, indifferent, carrying with it a history that could never be fully recovered, yet one that had reshaped the way humanity viewed the quiet travellers that occasionally crossed the Sun's domain. In the years that followed Atlas's passage through the solar system, the object settled into a peculiar place within the scientific record. It was no longer an active subject of debate, nor a source of speculation, nor a trigger for new observational campaigns. Instead, it became a reference, a point of calibration for how scientists approached the next generation of interstellar discoveries. Its legacy grew not from any single anomaly it exhibited, but from the cumulative influence of its uncertainties. Atlas had resisted complete explanation, and in doing so, it encouraged a refinement of the tools and assumptions used to study objects forged beyond the Sun. As new analyses emerged, a consensus formed around an idea that had begun quietly during its outbound phase. Atlas had forced researchers to reconsider what a typical interstellar object might look like. One had challenged expectations by lacking a coma. Borisov had challenged them by behaving almost exactly like a conventional comet. Atlas challenged them by doing both, displaying familiar signatures while layered with subtle complexities that did not fit neatly into existing categories. The lesson was simple expectations built on a sample size of 2 were inherently fragile. Diversity, not uniformity, defined the population of objects arriving from the galaxy beyond. The most significant long-term impact of Atlas lay not in theories about its origin, but in the infrastructure built to observe its successors. The experience demonstrated the importance of continuous multi-instrument monitoring, particularly during perihelion passages or periods of solar conjunction. It highlighted the need for more spacecraft positioned throughout the inner solar system, capable of providing uninterrupted coverage when Earth-based observatories fell blind. Missions that once seemed impractical, placing telescopes in solar orbit, deploying heliocentric sensor arrays, or maintaining dedicated interstellar object monitoring platforms, began to appear in early design proposals. In this sense, Atlas helped shift priorities, even if indirectly. Meanwhile, theoretical models advanced as well. The object's low, non-gravitational acceleration encouraged deeper study into how volatile release behaved under interstellar conditions. Its chemical composition informed simulations of planet formation in carbon-rich environments. Its early brightness anomaly prompted revisions to coma evolution models for objects entering a warmer system after eons in deep cold. Each refinement chipped away at previous assumptions, extending the predictive power of existing frameworks and preparing them for the next unexpected case. Yet the most enduring aspect of Atlas's legacy was not technical, it was conceptual. Scientists recognized that some of the object's behaviors remained beyond definitive reconstruction. The hidden interval behind the Sun created gaps that no retrospective analysis could fill. the object's rotation, thermal evolution, and internal structure would remain unsettled questions. This incompleteness became part of the story, not a flaw in the scientific process, but a reminder of the realities of observational limitations. Astronomy, like all empirical disciplines, operated within constraints, and sometimes even the best observations left meaningful uncertainties behind. Eventually, Atlas became a fixture in discussions about scientific method, as much as it was in discussions about interstellar matter. It served as an example of how to question data without sensationalism, how to entertain hypotheses without overcommitting to them, and how to maintain intellectual flexibility while adhering to empirical discipline. It illustrated the balance between skepticism and openness, an equilibrium essential for navigating an era in which new phenomena emerged more rapidly than interpretive frameworks could adapt. As for the object itself, it continued on its trajectory through the galaxy, silent, unchanged, and unobserved. Whatever history it carried from its unknown place of origin drifted with it encoded in its structure, but inaccessible to human instruments. That distance, both literal and conceptual, became part of its meaning. The object reminded scientists that they could extract only fragments of information from such visitors, and that understanding would always remain partial. Yet such partial knowledge remained valuable, forming the foundation upon which future discoveries rested. In the end, Atlas's significance did not lie in whether it was entirely typical or quietly unusual, nor in whether it resolved more questions than it raised. Its importance lay in how it prompted researchers to improve their tools, refine their reasoning, and recalibrate their expectations. It lived at the boundary between what could be explained and what remained elusive, a boundary that defined much of astronomy itself. Long after it faded into the cold distances beyond the heliosphere, Atlas remained a quiet presence in the scientific imagination. It had passed close enough for humans to witness, yet far enough to retain its silence. It had presented questions without insisting on answers. For a brief moment it crossed paths with the sun, left behind a trail of data, and then slipped back into the vastness that shaped it. And in that passage it left a final unspoken reminder, a principle that endured long after the last observation was logged. There would always be more to see, more to learn, and more to wonder about, as long as the galaxy continued sending its quiet travellers through the space between stars. Traveller, as our time together grows quiet again, we step back from the long arc of Atlas's journey and return to the small world beneath our feet. We traced its strange orbit, its impossible coincidences, its whispered anomalies, and now for a moment all of it settles around us like dust in the dark. What it truly is remains unwritten, and that uncertainty is its own kind of gift. Tonight you and I observed something far larger than an object in motion. We observed the way mystery moves through a universe that rarely explains itself. We observed our own curiosity, soft, persistent, fragile, and unbelievably human. And as Atlas drifts onward, hidden forces still shaping its path, the story continues without rushing. Somewhere beyond the sun's glare, new answers are forming and new questions with them. That is the rhythm of the Cosmos Observer, quiet, ancient, unhurried. Thank you for drifting through this silence with me, for listening, for wondering. If this story kept you company tonight, you're welcome to stay for the next. But for now, let your thoughts dim like a fading comet. Let your breath match the slow turning of the stars. Rest well, traveller. Stay curious. The universe will keep watch while you sleep.